Coming to the preparations and properties of phenol. Before starting the preparation and properties of phenol, let us see the resonance in phenol. Now, first of all, this CH pi bond, here the arrow starts from the upper bond, it is considered as the pi bond. So that lower bond is the sigma bond. This pi bond polarizes in this direction, in the sense it ionizes in this direction, so that a positive charge is obtained at carbon 1 and at carbon 6 a negative charge is obtained. Now carbon 1 will possess a vacant orbital in which this lone pair is coordinated, in the sense this vacant orbital of carbon and the filled orbital of oxygen will overlap in a parallel manner so as to get a pi bond here. Now, oxygen atom was originally sp3 hybridized. It changes its hybridization to sp2 in this structure. Now, when a pi bond is formed between carbon 1 and oxygen, the oxygen carries a positive charge because one electron of oxygen is given to the positive carbon at position 1, and then they get a pi bond and a positive charge over oxygen atom, and carbon 6 possesses a lone pair of electron and hence a negative charge. So the canonical structure obtained will be having this structure. Now, a negative charge means there is a pair of electron in an orbital. Now, if we assume that this carbon is sp2 hybridized and an orbital possessing a lone pair of electron, now the shifting of this pair of electron and simultaneous shift here will repeat. So that we have now a lone pair orbital here and the carbon is assumed to be sp2, and this pi bond ionizes in this direction, in the sense the orbital of this carbon gains a pair of electron and the orbital of this carbon, that is carbon 5 is left with an orbital which is vacant and possessing a positive charge. So the lone pair orbital over carbon 6, and if the carbon is assumed to be sp2 hybridized, will overlap with the vacant orbital of carbon 5 having a positive charge, and these two orbitals are perpendicular to the plane of the paper, and so they are mutually parallel and a pi bond will be formed between them. And here carbon 4 possesses a negative charge and a lone pair orbital, and if this carbon is assumed to be sp2 hybridized, then the lone pair orbital will be perpendicular to the plane of the paper. Now the same thing repeats here also. This pi bond here ionizes in this direction, so we get a lone pair orbital which is perpendicular to the plane of the benzene ring or the paper if the carbon is sp2 hybridized. Now here we get a vacant orbital and a positive charge over the carbon. Now this lone pair orbital and this vacant orbital are mutually parallel and they can overlap to form a pi bond here, and this position, that is the carbon here, will possess a lone pair orbital which is perpendicular to the plane of the paper if the carbon is assumed to be sp2 hybridized, and a negative charge will be obtained by this carbon. Now this lone pair orbital and the carbon possessing negative charge. Then if this pi bond is ionizing in this direction, means the electron pair in this bond is taken up by the orbital of oxygen. Then we get a neutral charge here because this oxygen atom gets the share of this carbon, and this carbon possesses a vacant orbital and again positive charge to this carbon. Now the negative charge here and positive charge here can be neutralized by overlap of this lone pair orbital here and the vacant orbital here. A pi bond will be formed since these two orbitals are perpendicular to the plane of the paper, and so mutual neutralization of charge occurs and we get a pi bond here, and the phenol original structure is retained, but you notice the point that here the pi bonds are arranged in this manner and here the pi bonds are arranged in this manner, so we get the resonance structure of benzene here. Now suppose phenol ionizes to give the anion and H positive. Now the OH bond ionizes so that we get O negative and H positive. Now this ion is called phenoxide ion. Now phenoxide ion also can undergo resonance. Here the negative charge shifts in this direction, means a lone pair of oxygen atom is forming a bond between the oxygen and this carbon, and for that initially this bond pi bond ionizes and we get a vacant orbital here, and the filled orbital of oxygen atom overlaps in a parallel manner to get a pi bond between oxygen and carbon, and the charge over oxygen atom is neutralized because one electron is given to this positive carbon, and when this ionizes we get a lone pair orbital here, and that orbital, if this carbon is assumed to be sp2, will be perpendicular to the plane of the paper. Now we get a negative charge, and the negative charge means always a lone pair. Now when this bond, this pi bond here ionizes like this, we get a positive charge here and a vacant orbital which is perpendicular to the plane of the paper. Now here we have a filled orbital perpendicular to the plane of the paper, so these two orbitals are parallel, and when they overlap the lone pair is coordinated to the vacant orbital here, means one electron of the lone pair is given to this carbon, so that the negative charge neutralizes here and the positive charge also neutralizes here, and we get a pair of electron here and a negative charge here. Now the same thing is repeated here and we get negative charge here and a pi bond here. Now when this pi bond goes entirely into the orbital of oxygen atom, we get a positive carbon here and a vacant orbital, and oxygen becomes negative, and this vacant orbital having positive charge when overlaps with the filled orbital here, we get a pi bond and the charges are neutralized because one electron of this lone pair is given to this carbon, and phenoxide ion is also a resonance hybrid. Now the thing is that the phenol resonating structures contain two charges. Now separation of charges and increase in number of charges make the canonical structures unstable. So two charges means instability is high, right? Whereas phenoxide contain only one charge. So compared to the canonical structures of free phenol, the phenoxide canonical structures are more stable because the number of charges is decreased in phenoxide. So we say phenoxide is more stabilized by resonance than phenol. So that the resonance hybrid of phenol will be having a higher free energy than the resonance hybrid of phenoxide. So phenoxide is more stable, and more stable the phenoxide, more is the tendency of formation of phenoxide from phenol, so that more is the tendency of formation of H positive. So we say phenol is acidic, and the only reason is that Phenoxide ion is more resonance stabilized than phenol. That is the only reason for the acidic nature of phenol. So that is the most important point regarding phenol. It is acidic in character. It is more acidic than alcohol because there is resonance stabilization of the phenoxide ion, which is more resonance stabilized than free phenol, unionized phenol, and that is again due to the canonical structures of phenoxide contain only one charge, whereas the canonical structures of phenol contain two charges, and charge structures are unstable. Greater the number of charges, higher will be the instability. Now coming to the methods of preparation of phenol. Now the first method is this one. Benzene is dissolved in fuming sulfuric acid, and fuming sulfuric acid is called oleum, O-L-E-U-M, oleum. Oleum is obtained by dissolving sulfur trioxide gas in concentrated sulfuric acid so that the acid fumes like concentrated hydrochloric acid. So fumes are observed due to the presence of dissolved sulfur trioxide gas, and here benzene sulfonic acid is formed. Now the product is this one, benzene Now sulfur trioxide is actually the electrophile there. Now the SO bond ionizes as S positive and O negative, and this pi bond connects to the sulfur atom through one of the carbon atoms, maybe through this carbon or through this carbon. Now suppose the pi bond ionizes in this direction, and so we get a positive charge here and a negative charge here. So this orbital overlaps with the vacant orbital formed over sulfur. Then we get a bond and a positive charge here. Now this is a carbocation, and its charge is neutral, of course, because there is negative and positive charges, but there is positive charge over carbon, so we can consider it as a carbocation. Anyway, the net charge is 0. Now this carbocationic part is stabilized by resonance, as usual in the case of electrophilic substitution reactions, so that this positive charge may be delocalized over the benzene ring system except this carbon, which is a saturated carbon. Now this carbocationic part then changes to the benzenoid structure, which is more stable than this one by shifting of a CH bond in this direction, so that this pair of electron now becomes the bond here, so that the share of electron of hydrogen is obtained by this carbon, and the positive charge is getting neutralized, and this H positive released will combine with the negative charge, and here the negative charge is over oxygen, so it becomes OH, and the structure is SO3OH, and that is benzene sulfonic acid. So sulfur trioxide acting as the electrophile, formation of an intermediate carbocationic part which is stabilized by resonance, not so stabilized as in the case of benzene, so it easily gets converted to the benzenoid structure by removal of H as H positive, and this H positive combines with O negative to form OH, and the group SO3H is formed. Now benzene sulfonic acid is also stabilized by resonance, and this group contain more electronegative atoms, oxygen atoms, so it shows minus mesomeric effect and minus I effect. So that this pi bond may shift in this direction, and simultaneous ionization of this SO bond occurs, and we get O negative double bond here and a positive charge here. And again we can draw more canonical structures. By shift of this bond we get positive charge here, by shift of this bond we get positive charge here, and again this pi bond shift can also result in the ionization of this SO bond, pi bond. So the oxygen atom here or oxygen atom here can carry the negative charge. So in the resonance hybrid, the two oxygen atoms will carry negative charge, partial negative charge, and the benzene ring will carry positive charges in the ortho and para positions with respect to the sulfonic acid group, so that the SO bond is having partial double bond character, or SO bond is strengthened. Now the net reaction may be written as benzene plus SO3 in presence of H2SO4. This carbon to H bond is broken, and SO3 is getting connected to this carbon, and H is connected to oxygen, and we get SO3H. So that is the net reaction symbol. Now SO3H is a highly electron withdrawing group, so that this carbon will have positive character due to the electron withdrawing nature of SO3H by minus M and minus I effects. Already we know the ortho and para positions are having positive charge. By minus I effect, this point may have a slight positive charge. So electron density is withdrawn from the ring, making the ring deficient in electron density, so that a nucleophile OH negative can attack this structure. Now when OH negative attacks this carbon 1, the pi bond here ionizes, we get a negative charge here, and we get a bond between OH and this carbon and the already present SO bond in SO3H. Now this anionic part is also stabilized by resonance, and this negative charge may shift in this direction with the simultaneous ionization of this bond, so that the negative charge comes here, and when this negative charge forms a bond here, means a lone pair bond forms a bond here, this bond ionizes to give a negative charge here and a lone pair, of course, so that the negative charge can be delocalized over the system, excluding this carbon, so that this carbanion, it is called an anion, carbanion, is also stabilized by resonance, and this is a nucleophilic attack where the nucleophile is OH negative. And carbon 1 possesses positive charge due to the minus I effect of the SO3H group, and OH negative prefers to attack the position 1 due to this partial positive charge, and again due to stabilization of the negative charge by delocalization over the remaining part of the benzene ring system. Now the intermediate, this is an intermediate carbanion intermediate, is not so stable as the benzene ring system, so this will show a tendency to get converted into the benzenoid structure. Now for that, this carbon should eliminate one of the groups. Now carbon to oxygen bond is stronger than carbon to sulfur bond because sulfur belongs to the third period, and sulfur atom will possess a 3p orbital, hybridized 3p orbital for bonding with the 2p hybrid orbital of carbon. Since an orbital in the third shell will have lower electron density, and again the overlapped region is having a lower electron density, the s2 carbon bond, the CS bond is weaker, so it is easily broken away from the structure, so that this pair of electron goes with the sulfur atom as SO3H negative, and OH is getting connected here, and this lone pair forms a bond here. So when SO3H is removed, we get a positive charge here, and that is neutralized by the pair of electron forming a bond here, that is shown by an arrow starting from the negative charge. Then we get OH here, and I told you earlier that phenol is acidic, so it will react with a base producing its salt O negative Na positive, so that H and OH combine to form water. And then addition of a stronger acid, hydrochloric acid, will dissociate this into free phenol and the corresponding salt. Suppose we are adding H positive, Cl negative, we get OH and NaCl. So acidification with a strong mineral acid like sulfuric acid or hydrochloric acid, the free phenol is liberated. Now the method is, first of all, treating benzene with fuming sulfuric acid, and the benzene sulfonic acid formed is heated with the molten sodium hydroxide. So extreme conditions are needed here: molten sodium hydroxide and fuming sulfuric acid. So this is also a method of manufacture of phenol. Then what happens to the SO3H minus group? SO3H minus group is having this structure as double bond OH with a negative charge over sulfur, and when this pair of electron is going along with sulfur, there will be a lone pair of electron over sulfur. Now this sulfur atom with the negative charge is little unstable because it is the less electronegative atom, that is sulfur, is carrying the negative charge. The system will prefer the negative charge over a more electronegative atom like oxygen, so that the S double bond polarizes to give O negative, but the lone pair will be here, but there is no charge because one electron of sulfur is taken up by oxygen and forms a pair of electron here and a negative charge, and negative charge indicates there is a pair of electron. Now with the Na positive in the medium supplied by NaOH, the sodium salt is formed. Now this is an acidic OH, so with the NaOH this ionizers are so negative. Na positive is connected to O negative, HOH is removed, so it forms O negative, Na positive, and this compound is Na2SO3, that is sodium sulfide. So the net reaction may be written as C6H5SO3H 3NaOH C6H5ONa plus Na2SO3 plus 2H2O. That is an equation, simple equation for the entire process may be summed up in this equation, and sodium phenoxide on reaction with the hydrochloric acid or dilute sulfuric acid, we get the free phenol. Now phenol is less acidic than hydrochloric acid or sulfuric acid, and phenol is also less acidic than even the carboxylic acids. RCOOH, so a group COOH is more acidic than phenol, and again phenol is less acidic than carbonic acid, which is H2CO3. So phenol is less acidic than RCOOH, less acidic than carbonic acid, etc. So that when you mix the sodium salt with the RCOOH or H2CO3, we are able to get the free phenol. Now that is sulfonation reaction followed by fusion with sodium hydroxide. Now the laboratory, benzene diazonium chloride, abbreviated as BDC, may be used for preparing phenol. Now benzene diazonium chloride, we have seen it earlier in which reaction? In Sandmeyer reaction. Aniline, the primary amine, is treated with sodium nitrite and HCl below 5 degrees Celsius. Then we get benzene diazonium chloride. Azo indicates nitrogen, diazo indicates 2 nitrogen, and the structure is N2 positive Cl negative, C6H5 N2 positive Cl negative, that is benzene diazonium chloride. Now this diazonium ion can take up electron density from the benzene by minus M effect and minus I effect, because nitrogen positive is much more electronegative than carbon, and there is triple bond of nitrogen which is much more electronegative. So this N2 positive group as a whole is highly electronegative, so that the alpha carbon will possess positive charge, and water can act as a nucleophile in this reaction. And N2 positive is a good leaving group. The quality of a good leaving group is that it is stable as a free entity, free species. Now N2 positive and takes up one pair of electron, it becomes N2 molecule, that is nitrogen gas, and nitrogen gas is highly stable, least reactive. Similarly, OH2 positive and takes up a pair of electron, we get a stable molecule water. So OH2 positive, N2 positive, etc. are good leaving groups, we say. Now here the nucleophilic attack occurs over carbon 1, that is alpha carbon, means the carbon connected to N2 positive. So that oxygen possesses a positive charge, and to maintain the valency, the pi bond here ionizes, polarizes in this direction, so that the ortho position is made negative and the lone pair is there. Now a CN bond is weaker than a CO bond. As the electronegativity of the atom increases, the partial ionic character of covalent bonds increases, and higher the partial ionic character, higher is the strength of a covalent bond. And since N2 positive is a good leaving group, This pair of electron is entirely taken up by N2 positive, so that nitrogen gets the share of this carbon and the positive charge is getting neutralized, and this carbon gains a positive charge, neutralize the positive charge. This pair of electron is shifting in between these 2 points, and we get OH2 positive, which can remove an H positive by shifting of this bonding pair over oxygen atom, in the sense oxygen atom taking up the complete pair of electron in its orbital, and we get the OH group. So phenol is produced when benzene diazonium chloride is warmed with water. Then the manufacture of phenol, there are 2 methods, and one method is called Dow's process. Dow's process we have seen earlier, that is chlorobenzene is treated with sodium hydroxide. Extreme conditions are used. Fused sodium hydroxide at 620 Kelvin and 320 atmospheres of pressure. Then as usual, the free phenol will be formed, but the phenol will react with the sodium hydroxide, producing the sodium salt, which can be acidified with the acid HCl or H2SO4 to get the free phenol. The simple reaction is removal of NH and formation of OH. That you must remember that this OH is acidic, so it will react with NaOH, producing O minus Na positive, and then you have to treat it with HCl to get the free phenol. So that is one method of manufacture. And then another important method of manufacture, which is widely used worldwide production of phenol, is from a compound called cumene. Cumene is isopropyl benzene, that is cumene, and there is a CH bond in cumene. The CH bond isopropyl group. Now oxygen is O double bond O. When the pi bond breaks, we get oxygen with valencies, one oxygen atom possessing one valency and the other oxygen possessing valency. Now the CH bond breaks, and the valency of oxygen is connected to this carbon, and then valency of hydrogen is connected to this oxygen. So we get this structure, which is similar to the structure of hydrogen peroxide. So we call it cumene. Hydro, because there is one hydrogen, hydro peroxide. Now cumene hydroperoxide, this reaction is conducted in presence of air, alkali, and at a temperature of 130 degrees Celsius. Cumene hydroperoxide dissociates in such a manner that this bond is getting broken, valency over oxygen, valency over carbon, they combine to form a pi bond, and we get C double bond O, CH3, C double bond O, CH3 is called acetone, and the valency of this oxygen, the valency of the benzene ring combine to form phenol. So cumene hydroperoxide decomposes, giving phenol and acetone as the product, and this reaction is catalyzed by acid. So in presence of acid medium, this reaction occurs. And then coming to the mechanism of conversion of cumene hydroperoxide into acetone and phenol. Now this is cumene hydroperoxide. In presence of acid, H positive is getting connected to oxygen atom through the lone pair. We get OH2 positive. Now OH2 positive is a good leaving group, so that it will take up this pair of electron towards itself, so that positive charge will be created over this oxygen. Now what happens is that the benzene ring with this bonding pair of electron will move towards this oxygen. So it is something called a 1-2 shift. A 1-2 shift. So that now the phenyl group is connected to oxygen atom. Since this pair of electron is withdrawn and connected to this positive oxygen obtained by removal of this pair of electron, this carbon atom gets a positive charge, and O is connected to phenol. So you simply remove this phenyl ring and connect this phenyl ring to oxygen atom through this bond, so that the carbon loses its share and gets a positive charge. So that is one step of the reaction. Now this positive carbon absorbs a molecule of water and then removes H as H positive, because when water attacks this point, the positive charge will be taken up by oxygen. And when OH2, so this will be remaining as C bond OH2 positive. When the bonding pair of electron in the OH bond is withdrawn by oxygen, it neutralizes its charge and H positive is removed, so that we get an OH group connected to the positive carbon. This positive carbon ultimately gets connected to an OH group. Now this bond rotates through 90 degrees, so that C double bond O is formed. Then the valency of carbon increases. To decrease the valency, this bond rotates through 90 degrees and forms a bond between H and O. Here when this bond is shifted, we get H positive, and when this bond is shifted, the charge of H positive is neutralized, because the share of this carbon is given to hydrogen. So we get acetone and phenol. So that is the mechanism of conversion of timine hydroperoxide into phenol and acetone, and this is the worldwide method of production of phenol from timine, that is isopropyl benzene. So that is enough. Thank you.